Okay, so we're on page 48, doing the chapter 3 discussion questions. I'm skip a couple of them, but go through most. Okay, number 1, Wes. Focus the most. Wes isn't even on the right page. Good. Good start. 48. All right, number 1. It says displacement vector n points from coordinates 5, 3 to coordinates 7, 6 in the xy plane. Which of the following displacement vectors are equivalent to n? Vector A, which points from blah, blah, blah to blah, blah, blah. B or C. And how would you do it, really?
Well, I would go with A.
Okay, A sounds good. Why? Why? What are you checking for? What are you doing?
Basically, when you have the first one going to 5, so that so you have 6, -4, just going up to 6, 3, -5, -3. So I guess it's kind of like the I and the J.
Okay, very good. So you're figuring out the individual displacements. You know, you have to figure out what n is first. So good, you were saying you're subtracting. There's a difference of 2 in the x direction and a difference of 3 in the y direction. So that's what you're looking for in any of them. You're just subtracting final minus initial. Which ones did you say were the answer? Okay, A is definitely the answer. I'll go through that one just as one example. The final, though, is the -4, -2. The initial was -6, -5. So, you know, we're subtracting, so minus the minus would give you the same displacement vector. Okay, so A is correct. Anyone see? There's one more that's correct. Yeah, B is correct too if you wanted to subtract. That's okay. You knew how to do it. C ends up giving you negative answers, so it's not C, although the magnitudes are still 2 and 3. Okay, so number 1. Number 2, Tyler. All right. This says if D equals A plus B minus C. Let's write that one on the board. And these are all written in bold, so you're assuming these are vectors. And you can add them and subtract them just like variables. So Tyler, which other statement there would be true? Or would any of them be true? If we're starting with what's written on the board, can you rearrange and come up with A? Which says A minus D equals C minus B.
Yeah.
Yes. Yes, you can rearrange to still get the original equation. All right, what about B? Yep. You can rearrange B as well to get back to what you started with. And what about C? Yeah, if you get... Yeah, D will not work. If you move D over... Or I'm sorry, C will not work because if you move vector D over to the other side so that it's positive, you don't really end up with that A plus B minus C. Okay, so only A and B work out there for number 2. But important to know we can follow our, common adding and subtracting rules for vectors. All right, Marcella, number 3. It says, equation 3-2 shows the addition of two vectors A and B is commutative. Does that mean subtraction is commutative as well, so that A minus B equals B minus A. Would that be true for vectors? No, we cannot do that, and that's why like C was wrong for the problem Tyler just did. You certainly cannot say that A minus B equals B minus C. I'm trying to think of a case where that might work, but it certainly wouldn't always work, or would rarely work. Is there an example of where that could work?
I think it would be
The same number? Because you'd end up... Yeah, but then you'd still have... So like... Yeah, but if they're vectors, the direction matters, so you couldn't say like 8 east minus 6 east equals 6 east minus 8 east. You get the same magnitude, but your directions wouldn't work out. Okay, so good. The answer is no. That does not work. All right, I'm going to skip number 4. Number 5, though, and you kind of had a question like number 5 as well. Connor, you got number 5. So it says, describe two vectors A and B such that vector A plus vector B equals vector C, and then the way they wrote it, so it's not in bold, magnitude of A plus magnitude of B equals magnitude of C. Of course, remember, direction matters, so how could we actually draw out vectors so that A plus B equals C sort of in our drawing, and the magnitude A plus B equals C? All right, skip that one for a second. Do the last one, part C of that. Because we had a homework quiz like this. A plus B equals C, and A squared plus B squared equals C squared as far as the magnitudes go. How would you draw that? Like, how would that work out? Okay, and what would the drawing look like? Exactly. Okay. Yeah. So that would have to be a right triangle scenario. So this A, head to tail, add B, resultant tail the first, head the last, there's C. So these are all the vectors, and yes, also, of course, it is true that the magnitudes are equal like that through a Pythagorean theorem. Okay, so that would be a case for the answer to C. Let's go back to A. You're making it maybe more complicated than it needs to be. And, well, I mean, this is added head to tail.
In a straight line.
In a straight line. Yeah, perfect. Yeah. So, of course, C would be the whole thing. So, yeah, it would certainly be true here that A plus B equals C as far as the magnitudes go. All right, how about the last one? What about B? It's kind of a tricky one. Well, it's the easy answer, but it's a trick question. This is really going back to like Maricella's question 3. If A plus B equals something, it can't be that A minus B equals the same thing unless what is simply true of B. If it doesn't exist, if it's 0. If vector B is nothing, but then of course why would you call it vector B if it's 0? So the only way that would work out is if B was nothing. Okay, Emily, you got number 6. Okay, can a vector have 0 magnitude if one of its components is not 0? Give me an example. Okay, but just one vector, not the addition of two vectors. Just can the magnitude of, sorry? Did I read the wrong one? Number 6. Can a vector have 0 magnitude if one of its components is not 0? No. So long as one of its components is not 0, it's not 0. Now, if you're thinking like 4 east, 4 west, yeah, that's all just x direction. Components are perpendicular, so as soon as you have one, you have some magnitude. All right, B. Can two vectors having different magnitudes be combined to give a vector sum of 0? Okay, if they're opposite directions, but it says they have different magnitudes, then no. Because we could go 4 east, and then we could go back west, but if it's not the same magnitude, there's no way of getting back to that starting point. So no. Okay, can 3 vectors give a vector sum of 0 if they're in the same plane? Meaning, like, just sort of ignore the z-axis for a second. Any x and y components are fine, but is there any way I can add up 3 vectors and have a vector sum of 0?
Yeah. Yes.
Sure. But they couldn't all be in the same line, obviously. I mean, you could do A, B, and then backwards. Still adding head to tail, C. Now there's really no resultant. Tail to first, head to last is the same. It's right there.
So I guess if C was something,
Well, be careful saying that because the resultant of A plus B is
the opposite direction, I guess.
this direction. I'm just adding a third vector head to tail. So this one, and then this one. All right, and okay, so yes, if they are in the same plane. What if they are not in the same plane?
So that's like saying Z.
Yeah, there's a Z component.
Yeah. I mean, you should do like the same like type thing, but with the C is on the Z. Oh man, I'm having a picture of the Z axis.
Yeah, it's hard to picture three-dimensionally.
No, it's like bottom. Because if it was coming out and the other black.
Yeah, if you have,
What could all of the vectors have an X, Y, and Z value?
what if they all had an x, y, and z value?
Because then, same thing, yes, you could just make it.
It just be out there.
Yeah. Yeah, it's like just out.
If they all had an x, y, and z value, then you, and obviously that's not a good three-dimensional picture. But yeah, if they all had an x, y, and z value, you could. But to actually answer this question where it says, can 3 vectors give a vector sum of 0 if they are not in the same plane? They're in the same plane, yes.
So I guess if that's the same thing again, the x and
Yeah, like it's saying,
So that'd be 1 and just an X.
yeah.
that's a no.
So that's a no, because there's no way to cancel out that like third dimension without another one in that third dimension. Yes.
Why couldn't you do when you were trying to get them to add up to 0 and the same plane, why couldn't you do them in a straight line? If A and B are like
I'm saying you're adding 3 vectors, not the resultant is the third vector. So here's A plus B. You know, I can add on a C. This point is not back here.
If your C though is like negative,
your C
whatever
in
A
the
plus
opposite
B is.
direction?
Yeah, that's what I was thinking. Like say A was 4, B was 2, and C was like -6.
Which part? Okay, but B says,
Or no, part.
I mean, if they were 3 vectors, sure. If it says for part B, can 2 vectors having different magnitudes be combined to give a vector sum of 0, then no. 3, sure. 2, no. Because it says, okay, 2 vectors of different magnitudes. I mean, how are you So there's A. Okay, here's B. Whichever way you want B to go, there's no way you can add it to A and get back to 0 if it has a different magnitude.
I was asking about the three vectors in the same plane.
That one's
You said it could be a straight line. Yeah, on the same line.
Oh, I see what you're saying. Yes, if it's 3 vectors, then that answer is fine too.
What about like the fourth dimension?
That just doesn't necessarily put you in a plane at all. Like if you're on the x-axis, I'm going to ignore the 4th dimension comment. To be in the xy plane, you need components x and y. Does that make sense? If you're in the xy plane, you have those components. You're parallel to the xy plane. You don't have a z component. Okay. So I'm moving on to 7, which maybe will answer one of those questions. Brandon. 7. Can the magnitude of the difference between 2 vectors ever be greater than the magnitude of one of the vectors? Oh, okay, let me keep reading. Can the magnitude of the difference between 2 vectors, so subtracting vectors, ever be greater than either A, the magnitude of one of the vectors, B, the magnitude of both the vectors, or C, the magnitude of their sum? And I'm going to give you a hint. All of these can be answered yes, and all of them can be answered yes with the same scenario. And you were almost kind of hinting at that scenario already. So let's think.
One being subtracted were like substantially longer than the one that you were subtracting it from. And it was longer than the first one.
Tell me about their directions, though. They're opposite directions and I'm subtracting them? Am I trying to get a bigger magnitude? Yeah. Okay, so let's say B is to the left, like that, and it says I want to subtract them. You know, what would that look like? And what my resultant? Sorry, am I subtracting that?
Yeah.
If I'm adding them head to tail, but I'm taking the negative of this, B should be going, actually, A minus B should look like this. And our resultant answer would be what? It would be 13 right, 13 east. So which scenario does that even answer? Can 2 vectors having different magnitudes be combined back on 7. Can the magnitude of the difference between 2 vectors ever be greater than the magnitude of one of the vectors? Sure. We just ended up with a magnitude of 13, but we started with 5 and 8. Okay, so there's A. Can the magnitude of the difference ever be greater than the magnitudes of both vectors? Yeah, it still is. How about greater than the magnitude of their sum?
Because when you add them, it'd be the negative.
There you go, yes, because we said the sum would have been 3. That was what I was accidentally doing the first time. Here is the sum of these 2 vectors, head to tail. Yeah, magnitude of B is 8, direction is to the left.
So it's negative.
Negative. So,
As a vector.
okay, so that scenario answered all of those questions. All right, 2 more. I want to do 8 and 11. All right, Thomas, you got number 8. Okay, similar type question. Can the sum of the magnitudes of two vectors ever be equal to the magnitude of the sum of the same two vectors? Yes. How?
So we're both positive.
Yes, if they're both in the same direction. I mean, if I have 5 and 8 to the right, the sum of the magnitudes would be 5 plus 8, will be 13. And it says, can that ever be equal to the magnitude of the sum of the same two vectors? So the magnitude of the sum, that would be the magnitude of the resultant. But that, of course, would also be 13. So if they're in the same line. Our subtraction example would not work. All right, and last but not least for chapter 3, Erica, you got number 11. All right, so in that picture for 11, it says, what are the signs of the x and y components of, to start, vector A? Just vector A.
Just vector A.
Yep, the components. What are the signs? Good. They're both negative. It's down and to the left. And then it says, what are the components? What are the signs of the components of vector D, where D is equal to vector A minus vector B? What would that even look like?
When B have the opposite direction.
Exactly. It'd be the same as adding B with the opposite direction.
So B is opposite direction.
So that was A. If you're adding B, which way? Or if you're adding the opposite of
Adding
B.
a straight down line.
Just adding a straight down line. So here's B. So vector D, which was A minus B, of course B was up originally, would be that. So what are the components of D? Still negative and negative. Okay, so those are the discussion questions I want to go through in chapter 3 for vectors.